what can we say about the longest run of baskets we might expect for this experiment for any given p? Well, we can reason as we did for experiment A previously. If I perform R trials of experiment AP for some given p, I expect that 1 minus p times R of the outcomes have no baskets whatsoever. 1 minus p times R of the trials will result in just a single miss. Therefore, I would expect that the other p times R outcomes have a run of baskets of at least 1. They're either a basket and a miss, or 2 baskets and a miss, or 3 baskets and a miss, etc., etc., etc. Out of those p times R outcomes, with a run of at least 1 basket, I expect, according to my distribution on the previous page, that p times 1 minus p times R of them have exactly 1 basket, a run of baskets of length 1. So I expect the total number minus the ones with a run of baskets of length exactly 1 to be equal to the number of outcomes which have runs of baskets of length 2 or more. And that results in p squared times R. That calculation is p times R minus p times 1 minus p times R, which amounts to p squared times R. So I expect p squared times R of the outcomes to have runs of baskets of length 2 or more. I can carry on in this way, and I find that I expect p cubed times R outcomes to have runs of baskets of length 3 or more, and p to the n times R outcomes to have runs of baskets of length n or more. So therefore, the length of the longest run of baskets in the data is going to be that number n, where p to the n times R rounds off to 1. So I expect one outcome to have length, a run of baskets of length n, and p to the n plus 1 times R rounds to 0. So I expect no outcomes to have a run of baskets of length n plus 1 or more. Now, I might find n by trial and error, but if you know a little bit about logarithms, then you could instead find an approximate solution to the equation p to the n times R equals 1. And so you're solving the equation p to the n equals 1 over R. I can apply the natural logarithm to both sides, solve for the n, and I get n is approximately equal to minus the natural log of R over the natural log of p. Now remember, I'm running R trials of experiment AP here. It's not the same as taking R shots. And also remember that natural logarithm function you can find on any scientific calculator. And so you can calculate this even if you don't see how I've solved it. Just for comparison, I simulated 50 trials of this experiment for a particular p, with p equal to 0.75 using Excel. So I generated data for 50 trials of experiment AP, basketball player, with a 75% chance of getting a basket on every shot, keeps taking shots until they miss a basket, and then one trial is over. Here's our data for a simulation of 50 trials. I've highlighted the longest run of baskets in the output, and it has length 17. Now, we would expect longer runs of baskets in this data than, say, the runs of heads that we might get if we flipped a coin, because the probability of success, or the probability of a basket, is greater than 0.5. It's 0.75 here. The question is, how does that longest run compare to what we might expect from our probability distribution calculations for AP? Well, what do we expect? out of 50 trials of experiment AP with p equal to 0.75, we would expect the longest run to have length approximately minus the natural logarithm of 50 divided by the natural logarithm of 0.75. That turns out to be approximately 13.598, or we can round it off to 14. Now the question is this run of 17 too long for randomly generated data? Well, obviously not, because this data was randomly generated. So what can we say here? We should expect some variability in the length of the longest run in randomly generated data. It's not necessarily going to be exactly minus the natural log of r over the natural log of p. There will be some variation. We'll think about this variation a little more in the next section when we study the standard deviation of a random variable.